All right, on tonight's episode of Python Papi, we're back inside our artificial intelligence course and we're still doing our learning module. Let's have a look at what we went over tonight. Now, last night, if you recall, the last thing we went over was the NIM game inside reinforcement learning, and tonight we're going to pick up where we left off. Now, NIM is a bit of an easy game to use reinforcement learning for because there are so few states. There are only states for how many different objects on each of these various different type piles. We might imagine that it is going to be harder if we think of a game like chess or games where there are many more states and many more actions we can imagine taking, where it's not going to be as easy to learn for every state and every action what the value is going to be. So oftentimes in that case, we can't necessarily learn exactly what the value is for every state and every action, but we can approximate it. So much as we saw with the mini-max, where we could use a depth learning approach to stop calculating at a certain point in time, we could do a similar type of approximation known as function approximation in a reinforcement learning context. So function approximation is approximating Q S of A, often by a function combining various features rather than storing one value for every state action pair. Where instead of learning a value of Q for every state and every action, we just have some function that estimates what the value is for taking this action in this particular state that might be based on various different features of the state of the environment that the agent happens to be in. Where we might have to choose what those functions actually are, but we can begin to learn some patterns that generalize beyond one specific state and one specific action. And we can begin to learn that certain features tend to be good things or bad things. Reinforcement learning can allow us to generalize beyond one particular state and say, if this other state looks kind of like this state, then maybe the similar types of actions that worked in one state will also work in another state as well. So this type of approach can be quite helpful as we begin to deal with reinforcement learning that exists in larger and larger state spaces, where it's just not feasible to explore all of the possible states that can actually exist. So there, so that, so there then are two of, so there then are two of the main categories of reinforcement learning: supervised learning, where we have labeled input and output pairs, and reinforcement learning, where an agent learns from rewards or punishments that it receives. The third major category of machine learning that we'll just touch on briefly is known as unsupervised learning. And unsupervised learning is giving input into data without any additional feedback or learned patterns. And unsupervised learning happens when we have data without any additional feedback, without labels. In the supervised learning case, all of our data had labels. We labeled the data point with whether that was a rainy day or not a rainy day, and using those labels, we were able to infer what the pattern was. Or we labeled data as a counterfeit bill or an authentic bill, and using those labels, we were able to draw inferences and patterns to figure out what does a banknote look like and what it doesn't. In unsupervised learning, we don't have any access to any of those labels, but we would still like to learn some of those patterns. And one of the tasks that we might want to perform in unsupervised learning is something like clustering. A clustering, organizing a set of objects into groups in such a way that similar objects tend to be in the same group. Now, I'm going to leave it there for now. We did take a lot more notes and we did end up doing some graphing and putting some things together, but I'm not going to dive into that tonight. But I will keep you posted every step of the way as usual. But for now, this is the Python Papi. You guys stay Gucci.